मतलब एक्टिव नहीं हो जाए.
What else was I going to say about assignment 2? That's right. Assignment 2 was a little bit disappointing in the amount of people that didn't put a design paragraph together on Moodle in the text box where I asked it to be put. It should have been placed in the text box on Moodle, which was part of the assignment. It should have.
The comment section.
Comment section, yeah. And also, as asked in class, there was one mark towards an introduction and a description of the site, and I said I was particularly looking for the mathematical side of things as well as a general description of what was going on. Secondly, issues. Probably looking for 3 to 5 issues and 3 to 5 ways around those issues as well. So to get your full 2 marks, that's what was required. It was a bit disappointing that only half actually bothered putting anything in the comment section. And the other disappointing thing was the multiple cross sections. That required you to do obviously some cross sections, including at least probably one at each side that's outside of the platform. The clever person would have done it right on one of the design contours so that you could have projected that line up as its own little platform to form the cross section. But the next bit was the disappointing bit. In class, on record, in the lecture, I asked for you to put everything into the prismoidal into the prismoidal calculation, and to copy the right-hand side of that into model space. I didn't want to see it in layout, just into model space. Also, I asked for it to be near the cross sections. I actually let people away with my marking that had put it 50 million miles down the road, where I had to go zoom extents, and there was a little dot here and another one down here. You will do, at some stage in your life, need to work out that a copy paste should be right beside the cross section. The other thing is, a screen capture didn't work. So for all those that put a JPEG in there, a screen capture, print screen, Control C. I'm sure you can see it on your home laptop or Unitech computer, but how about giving the file to your mate to open? I bet you they can't see it in there at all, and I couldn't either. So there was probably 10 students who'd done a screen capture, and I couldn't see anything, so that didn't count towards marks, I'm sorry, even if it was correct. And lastly, the one that I was hoping to trick up students on, I wasn't hoping to trick you with the other ones, the calculation towards compaction and forgotten, I'm having a little bit of a brain fart at the moment. Hold on a second. Compaction and bulking, yeah, sorry. So it will vary from year to year. So if you copied someone from last year that said, hey bro, this is easy to do, you just do this, it's quite possible you were wrong, because last year there was more fill than there was cut. If there's more cut, what you do is you apply the 1 point times the cut by 1.3 and times the fill by 1.25. Then you get a new balance at the end. It works out as roughly 5%, but it's a little bit different to 5%. So now, a lot of students very cleverly did that on their prismoidal calculation sheet. You've got Excel open, easy to do. Just put a couple more lines down the bottom. Whammo, you've got the whole thing. And in fact, they got it completely right. But I asked for it to be summarised in the notes section of the proposed plan. So that's where that should be. So it was really hard to get that. I think only 2 students managed to get that extra half mark. As far as the cross sections go, I'm nearly half the way through the diplomas. I've marked most of the cross sections. The biggest problem there was students not resetting their dimension arrows. They just left them at whatever it was, 3.5 or something like that. And if you'd had time, you'd have noticed that they were massive, huge arrows, and you would have gone, oh, I better change that. But of course, if you didn't have time, you wouldn't have had a moment to change that. 0.25 is not the answer either. It was 0.175. That was the text height and the arrow size. And disappointingly, quite a lot of students stuffed up their viewport scale because, for one reason or the other, they couldn't get everything in after they'd drawn it. And I'm going to tell you this now about assignment 3. When you've done your plan view of this, and you've got the reinforcing in place around it, and you've figured out what numbers go on top of the bars, you put your delimitator bars in, and you think you've done a really good drawing, please leave at least half an hour to move things around. Because one small delimitator line going through another bit of text means you move the delimitator line, which means it now goes through some more text. And you move the text down here, and all of a sudden another delimitator line is through that text. I do not allow text with an arrow pointing at the bar. Okay? So please allow at least half, I would say an hour, to shuffle it around, and it is very, very possible to do it. It's just that I'm giving you some real world learning here because that's what you have to do in an office where you're drawing up reinforcing. So let's bounce on to the notes. Structural steel. In New Zealand, structural steel is used quite a lot, but nowhere near as much as it is used in Europe and America. The reasons for using structural steel is normally it goes together a lot quicker, and in domestic builds you don't need to put nogs between the studs on a building. So you can put all your services down, you can put your power, your water, communications cables all down the wall very easily without the nogs sitting in place. Also, when it comes time to putting your drywall on, or what we call in New Zealand gypboard, that doesn't have a time period because once you're dried in, everything's dried. Tin dries straight away. You can fix to it. In a normal domestic build, you could be waiting anything up to 4 weeks for your moisture content of the timber to get down to a point where they can put the drywall on it. So speed is what it's all about in the construction game. So yeah, that's one of the main issues. It's not necessarily cheaper than concrete, but definitely the speed issue is one that comes into play. Also, a lot of steelwork can be prefabricated on site, in the factory. So I would suggest that this bridge that you're doing, good note as well, some parts of the steelwork would be prefabricated back in the workshop. The two angles at either end of the bridge would probably have the plate welded to them back in the workshop and set on site like that with the holes pre-drilled. With timber, that doesn't happen as much. We don't tend to pre-drill holes, we don't tend to pre-cut the timber except for maybe the length back at the sawmill. Basically it arrives in the length, big long lengths, and they chop it up on site to work it. So yes, the steel sort of fits together like a big Meccano set on site, and as long as you've got the right cranes and bits and pieces, it's not a problem. Incidentally, in Auckland at the moment, there's never been anywhere near as many cranes as there are around the place. I saw an article in the Herald the other day that said there was 140 cranes hanging around Auckland. which was a hell of a lot. When I first came back here in 1987, just before the share market crash, there was about 10, and people were saying, wow, what a go-ahead city this is. Mind you, they all came down pretty much straight after the crash. But so this sort of situation where cranes everywhere is predominantly quite common in Auckland. Most of our steel comes from the most popular grade of steel, which comes from a company called One Steel, is 300 plus. That's easy to remember because the most popular reinforcing bar was grade 300 as well. It replaced 250 in October 1994. So I guess any drawings pre-1994, isn't that long ago, will have different bars in any buildings that predate that as well. And the other thing which I've also asked a question on in the test is why did we replace it with 300 plus? And the answer is because it improved the performance, the weight performance of the steel by 20%, which means the new 300 plus steel can carry a load of 20% more. Now I've included here a little table of the different steel lengths members, and I'll talk about the members in a second, but I just want to say this as far as this table goes. In the past I've had students doing their structural steel assignment and they go back to this table and they start trying to work out what lengths are available and what they can use, etc., etc. This table is given to you for information only. You don't sweat it, you don't need to use it for your assignment. What you do need to appreciate, and it is one of my multi-choice questions also, is the fact that when you are doing steel design in any way, shape or form, you always ring up or go to the website of a company and get these tables. If you're in the process of designing for example, a building that's 7 meters by 7 meters, then you can look at this, and they're going to supply their smallest one is a 7.5 meter member, and if the member is the one that you've chosen, that's fine. But you might as well make the building another 0.5 longer, otherwise you're going to pay for them to cut that down to the right length. So a cost factor comes into play, and it's often to do with the length supplied. If I was to make that part of your assignment, you'll notice that 13.5 is a popular length, and we've made our bridge 13.2. So maybe you would think seriously about making the bridge just a little bit longer, because that's the size member that they produce in the factory. Secondly, if you're looking for a note to do with the steel on the job, that's a bloody long piece of steel. That's 13.2 meters. And you're going to need a big truck to carry that on site and a big crane to put it into place. So cost-wise, perhaps not the most effective way to do it, but at the end of the day, you've still got to draw it up like that. So I'm going to show you this briefly. This is, and I'm going to come back to it. These are nominal sizes, but what this is doing is it's showing us the previous call up for each member and how we call it up now. What do the members look like? Let's go over that. There's a little wee sketch of some of the more common ones. This is an angle. This is possibly a column rather than a beam. This is a flange, and those are hollow core beams or steel members. Here's a profile shape of them. This explains it a little bit better. A universal beam, or a UB as they're called, is quite a bit more skinnier than it is height. The height-wise is always quite a lot higher than it is skinnier. They do come fatter than that, but generally speaking, you'll recognise a beam because it's more like that shape. A column, which is this one here, which is normally used in a building to hold up the roof. In our case, we've used it on the bridge because I had to give you a bit of experience with columns. So it goes crossways across the bridge and holds the timber that fits on top of it. A column is normally very close, the dimensions B and D are very close to each other. So it almost looks square or rectangle. So you recognise the shape of the column very easily by that shape that you see there. A rolled steel joist tends to be fatter in this area up here. We haven't got one of those in our assignment, okay? But I'm telling you this because there may be a multi-choice question on those three items, and clearly there is quite a big difference between each of the three. The next members I'm going to talk about are the flange, and you'll notice that with a flange, it's kind of a sideways U, isn't it, in some ways, but we've got two types. There's a TFC and the PFC. And all sorts of problems with these things growing up these days, you don't know why. I'm going to exaggerate this a little bit, but you'll get the general idea. The TFC is this one, and the T stands for the word tapered. Tapered means it comes down to almost a point at the end. See the taper? In reality, it would probably come down with a little curve on the end. Okay. This one, the PFC stands for parallel. Parallel flange channel, tapered flange channel. Now the class exercise has got the flange on it. It's not that obvious that it's a tapered one, but just be aware that we don't have one in our assignment this year, but I'll still take you through the class exercise way of doing it. Angles. There's two types of angles, an equal angle and an unequal angle. You have got an equal angle in your assignment, 75 by 75, which means it's 75 that way and 75 that way. These two members I don't tend to recommend in construction that much. The only time when you might look at something like that is if, say, you were running refrigeration pipes for a supermarket through the inside of them, so you're utilising the space if you're tight for room. Generally speaking, we tend to use the other members in construction, but they're there anyway. Rectangular hollow section, RHS, and a circular hollow section. The T sections are equally as often, usually not used either. So the main ones you need to remember are universal beam, universal column, rolled steel channel, equal angle and unequal angle. And they're the most common, and of course the plate, which is, as I said, looking like that piece of paper with a bit of thickness on it. Now I'm going to go back up here, and I'm going to pose the question to you all. Why the hell would Roger include in his notes what we used to previously call up, how we used to previously call up some of these members? So for example, the universal beam, why would I say that it used to be called up by 760, 270, 244 GUB, whereas nowadays we call it up as 760 UB, 244. So why would I do that? That was the first person to say something. Test. Is it in the test? Yes, there is 3 questions from this little section of the test. Somebody here said something as well.
That's a shorter version instead of saying others dimensions.
Yeah, it is a shorter version, but why would I put previous in the... Yeah, we used to do it that way, now we've gone up down. Why would I... Yeah.
Because now we assume that the width is 270. So we don't need to write it anymore.
Sort of, but that's not the answer I'm after. I'm going there.
Would it be noted in previous plans if you pick up older plans?
I think that's probably close enough, actually. Yes.
He deserves a half.
He does. All right. So because of that, I'll give it to him, but he can give it to you for getting him the half mark.
So I can email you?
If you haven't already got one for this next assignment, email me. Okay. That's very good lateral thinking. I don't know what anyone further back was going to say, but basically the reason for that is there are a lot of old drawings out there. Okay. And just like old surveying drawings, you've got to sometimes do things in terms of you've got to be able to work out your dimensions and things. And for example, if we were adding on to this lecture theatre, one would think pretty simple job. We're just going to join on to whatever's here. We go down to council and we find this building was built in 1970 something. And all of the call up for everything, including the steel, is the old-fashioned way. So we quickly run back to Unitech and we say, Roger, how the hell do we do this? I can't do it. You're an old fart. You can do it for me. No, you don't do that. You look up Roger's old fart notes and you go, that's right. That's how it's all done. So I think it's important that these things at least stay there for some time while we still do this sort of thing in Auckland. Auckland, because of the price of buildings and everything, they tend to often not put the big swinging ball through them. They tend to just add on to them and do them up a little bit. So, yeah, very common. So common that I will ask you if you see anything on the assignment that is the old call-up. You know how I've done sketchy thing for you to follow? It's not as easy as you think. It's not just, nearly said it, which got me in trouble last time. It's not just copying what I've done. You've got to have a look at it, think about it, and do it the way it should be. So if, for example, my beams say are called up as 760 by 270 by 244, I would like you to pull that particular beam up as 760 UB 244. Right? You might find there's nothing like that. That's fine. I might have pulled them up the proper way. The other thing is the squiggly lines. I think I told you that last week. Don't draw them again, please. Do them the way you would have done them for Ingrid in semester 1. Nice lined up notes where possible with the arrows properly pointing to things. Look, if you don't know, I'm happy. If you've done it, the lab before, and you've completed it, I'm happy to take a look at your arrows. Happy to say yes, they're fine. Or no, there's a couple of problems there, go and change them. I may not even tell you which ones they are, but I'll at least highlight the fact that there's an issue. Yep.
KGUB, is that per
Kilograms,
universal beam?
universal beam, hold on. Yeah, kilograms universal beam. Sometimes, usually that's in kgs, normally in capitals, in little lowercase, and UB is normally in uppercase, so that's the fraction wrong. But yeah, the next one down is kg universal column. And the plates themselves, it's important to realise the plate is called up by width, by length, by thickness, and it's the same as the way we used to. So whatever I've called it up on the plans, that's how you regurgitate it on your notes. We will do a class exercise at the end of this, and we will quantify everything perfectly for you. And I think you'll be very confident that you can do the steel after that's been sewn. Riveting. Although it's not a common construction method today, it's absolutely everywhere all around the world. Whether you go to San Francisco and you look at their famous bridge, or whether you go just to Auckland Harbour Bridge and have a look, if you've ever walked over that or in that or around that, or been stuck in a traffic jam and have a look, you'll see rivets everywhere. The biggest problem with rivets is they become the construction weakness. I've actually asked a question on that as well. And that's where you're going to find rust starts appearing, that's where corrosion of the rivets start, and that's where they have to replace the rivets, and it's a costly expense. Construction-wise, it's very easy to put together. You do it very quickly. You've got a big rivet gun, you're walking around putting the rivets in, but the biggest problem with rivets, once again another question, is you have to coat them with paint. Corrosion-free paint. In fact, interesting, the San Francisco Bridge, and I'm trying to think of its name, which I've actually called the Golden Gate. Yeah, it's called the Golden Gate Bridge because it's kind of a golden rusty colour. When they built the bridge, they painted it with corrosion paint. Yeah, rust gold coloured orange paint, which at the time nobody wanted to see, but somehow the guy that was building it, they went over the cost, and he convinced the mayor or of San Francisco that was the beautiful architectural colour that they were going to do it, and they would continue to do it for the rest because they had lots and lots of cheap corrosion-free paint, and that's why it ended up orange. So they just continuously paint it with corrosion-free paint. Auckland Harbour Bridge is a separate exercise. You have to feel for the guy or girl that does it. They start at one end in January and they finish, and the next January they start at the other end again and keep painting it. It's a once-a-year paint job. I don't know how many do it, are on the bridge, but that's how long it takes to paint it, and then they start at the other end again. So, in the long term, bolting is a much better way of doing it. Welding is used more for site manufacture, for site welds. It is fairly rare to do welding on site, but they do use welding cutting machines on site. So the connection of choice for most engineers when they're doing any design is bolting. No, you can get like stainless steel bolts. Yeah. So they just basically, I don't know what the lifetime is. Maybe even longer. Yeah. Also, you can get engineering bolts. We'll talk about them in a minute, and high-strength bolts as well. So there's a lot of choice in bolting. Whereas I've never seen any rivets that are stainless steel. I think they basically start corrosing from the day you put it on. We are assuming that the bridge is over salt water. I mean, it could be over fresh water in the middle of the country somewhere where the corrosion factor is has been a problem. Anyway, this next paragraph forms another question, and it's to do with an engineer's choice of what members to use and what should be considered. So we're looking about the size of the member, the loading on the joints, the length of the member, the method of erection, and the most economical method of joining. So those 1, 2, 3, 4, 5 things form the basis for a multi-choice question. There's some references there to various standards as well, which may form part of your notes. Bolted joints. I guess this is a little bit out of date now because as of this year. I think he retired. Still got a lot of respect for him, but he might end up out of my notes next year. We'll see. He was hopeless. He was hopeless. He overran the ball a couple of times, and he looked like his fitness was hopeless. 100 metres, yeah. After that, he had nothing else. Sorry, we digress. Sorry. So let me see. With bolts, I'm opening this up to you guys. I've basically given you the size of the bolt. What you've got to do for your assignment is work out the length. So you've got to work out the length, type, and the strength. The type of bolt is highlighted behind me on the screen, and I would suggest the bolts that go down into the handrail should be more like this one here with a head on it that's rounded. Alternatively, the bolts that go through the deck should be recessed into the wood. So you would drill a hole, you would recess it in, you would put your socket on top and tighten it up, either from the bottom or the top or both. So you can get the boards really tightly fitting, but you want to recess it so that somebody walking along isn't going to trip on the bolt, especially a student running off to play volleyball with bare feet or jandals on. Okay. On the handrail, the last thing you want to be doing is walking along the bridge and cutting your fingers every time on the handrail. So you've got to think of the type of bolt which is best to go on. So that's the type of bolt. The length depends on what it's going through. Is it going through a piece this big or a piece this big? We generally have enough thread on the other end of our length to tighten it up. So the length is taken from this point here to the end of the thread. So when we talk about length, it's from where it goes through at that point right through to the very end. So if you've got a washer and a nut, you've got to have at least a wee bit of room at the end to tighten that up. And also there are situations where you don't want too much length because it'll be sticking out, and it may cause an issue if it sticks out too far as well. When we talk about the strength of the bolts, I'll just cut straight to the mustard here, which in New Zealand terms means most engineering is high strength bolts. We have commercial. It's important to understand that when you go to Bunnings or Mitre 10 and you've got a little fix-it job on a door or something, you're going to go into their commercial section and you'll see whole trays of bolts, and you work out which one you're going to want for your job, right? But they're the cheap ones. They're the ones that will cost the least because you don't want them outside, you don't want them holding anything up. When you start getting into commercial bolts, you're talking about big dollars. So, and it's a different section altogether of some of the hardware stores. There's different, you don't have to worry about this when you call it up for the drawings, but in terms of general knowledge, I'm covering these things as I'm going along because this is another great little section for a multi-choice question. And it's to do with the snug fit and the friction fit type joint. So your snug fit joint is always going to be a bolt in a hole which is 1 millimetre either side, right the way around. A friction type joint is going to be something like this. So you've got a bit of play over to where the bolt goes, and it's often used where you're lining it up with another bolt on the other side. You need a little bit of play to get it perfect. And also that joint allows a wee bit of movement, a bit of friction. where you know that the member's going to be expanding, contracting, or perhaps even moving at the same time. Okay. When we talk about putting holes into any of our members, there are some important terminology here. I can't remember which one I've asked the question on. I think it's pitch, but there is a question on one of those four things there that you're looking at. When we talk about pitch of holes in members, we're talking about the distance between the holes in this direction. So if it's a great big long bead, instead of saying, oh, the centres of the hole are, we say the pitch of the holes in that direction. Across, we call them the cross centres. At the end and the edge. The difference between the edge is the edges off to the side. The end is the very end of the steel member. You've got the end distance and the edge distance along the side. Okay? Yes. Yes. Now, in plate design, which I'm going to get into in a few seconds. Sorry, let's start with, that was beam design or angle column design. This is angle design. So with angles, it's slightly different. You've still got your pitch going this way, and you've still got your end distance. But the distance from the face to the hole, and from that face to the hole as well, is called a back mark. So that's interesting. There's back marks in surveying, which is totally different. And in dimensioning angles and members to the holes, we talk about back mark when it comes to angles. Plates. Plate design is something that I'm going to test you on in the test. There are 3 questions on it, and if you get these basic principles, they're 3 easy marks. So it's well worthwhile trying to understand what I'm about to say here.
कई बार हम भाई कितने सोचते हैं जैसे कि एक चीज़ होती है बहुत अच्छी फैसिलिटी है मगर उसको हम कुछ बकवास ले देने में मगर फैसिलिटी चीज़ नहीं है जैसे ये चीज़ फैसिलिटी
Before I do the example, I want to talk about why we do it. Okay, well, with plate design we have a minimum and we have a maximum. The minimum is the minimum distance between. The reason why we have a minimum is because otherwise this sort of thing happens. If we put it too close to the edge, you get end splits. If you put it too close together, you get plate bursting between the holes. The reason why we have a maximum is if your distance between the holes is too long, we get buckling or bursting. More like buckling.
Oh, sorry, that was a man.
So with plate design, we have very distinctive maximums and very distinctive minimums. The objective of plate design is to push these to the outside edge. Looks very similar to that, doesn't it? Close as we can to the outside edge. So the first thing we do is apply the minimum. The second thing we do is check the maximum. If it's too far apart, we bring it in. Okay, let's do one. 600 by 700. We have a 18 millimeter, no, Yes, we do. 18 millimeter bolt. No, we won't. Change that. Let's make a 14 millimeter bolt hole. And let's call it a 10 millimeter thick hole. Plate, sorry.
Is the maximum and minimum distance going from the center of the hole or the side of the hole?
Center to edge or center to center. So we've got a 14 millimeter bolt hole, we've got 10 millimeter thick plate. The plate is 700 by 600. We're attempting to put 4 bolts in there. The rules are specified here. The rules are quite simple. 2.5 times the nominal bolt diameter. So not the bolt hole. So what diameter would the bolt be? 10? No. It's 1 millimeter either side, so it'll be 12, right? So we better write that down. So that makes 12 diameter bolt. So it says here 2.5 times 12. What's that equal to? 2.5 times 12 equals 24, 30, right? Everybody else? 30? 30? Okay. So let's do this, start off with 30, because that's the idea, is trying to make 30 equal the plate design. So it's 30 all round. So far, so good. So what does that leave us here? 540 and 640, 540 and 640. Okay. What's the maximum? The maximum is 32 times T. 32 times T. Or 300, whatever's the smallest. So I'll just write that here. 32 times T or 300. What's T? What's thickness? I haven't told you the thickness yet, have I? I have 10 millimeters. So 32 times 10 equals 320. So therefore equals 300. Maximum 300. So now we're going to put the 300 here. And there. And there. And there. Which means, what does the 30 change to? 150? 150. 200. 200. 150. 300. 150. 200. So I'll just summarize what we just did. We started off by taking the minimum. If this distance had been about 400, then that's all we would have had to have done. But it's quite a big distance. So the minimum was okay, but unfortunately the middle distance was too much. Because we did our calc and 300 was all it should have been, so we brought it back. And we've ended up with 200, 300, 200, 200, 300, 200, 150, 300, 150. I'll do that again for a plate that is only 400 and 300. So we start off with 30 again. and that means that we end up with 340, 240,
So that's gonna be 300.
340, and 240, right? The 240 stays the same, that's fine, it doesn't move. The only one that moves is the 340, that goes to 300, and so therefore we've got 50 on each side. I think you guys are starting to get the hang of it now. 50, 300, 50. So I'm going to give you 3 of those questions in the test.
Oh,
Okay?
3 questions.
3 plate questions. And what I tend to do is I tend to have A, B, C, D, D, and you'll be asked for one of those. Okay?
बस हो
And
गए
the concept is relatively simple. You just need to get your head around how to do it.
आई मुझे
Your minimum and your maximum.
स्टे
If you don't know, you're welcome to ask me tonight. This also has a bearing on assignment 4 because you have a plate.
मैं पूछा था भाई 10 बार मैं पूछा भाई मुझे जाता किसने बोला
And you have 2 holes.
ला मैं क्या पेड़ में बैठ रहा कि भाई इसका
I will allow you to put those holes anywhere you like as long as they don't breach the minimum or the maximum. So it'll take you some work to figure that out. You'll have to move the holes around. You've also got the complication of this, which is the angle that is welded to it, looking down on it. Some people are trying to figure out what I've just done. Here's the plate here. Here's the angle.
Excuse me, this is a class, okay? And please be quiet.
The angle goes down like that, and there's another plate at the bottom. So the plate is welded on right the way around from the top and the bottom with a 6mm fillet weld. We'll talk about that in a minute as well. So looking down on that, you've also got your 2 holes, and you can put them anywhere you want around here as long as they don't breach the minimum or the maximum. And that's for assignment 4. So looking at that in detail, you'll be doing a little plan view like that. You'll have your dimensions to the holes, and maybe to that hole as well. And you'll also have a call up, so you would have to name the bolt that's going in there. You need to know the bolt hole size, and also you need to show the weld. Last year it was quite funny. I got someone on the sequel said, it's not fair the lecture effects on people with pants. That's what he said. Yeah, me too. When you show a plan view of welding, it looks like nobody's beard in here. It looks like a schoolboy's beard. That's just about a 3rd or 4th former at schoolboy. So just little speckles, all right? So that if I glue that up, it looks more like that. And I'm sure you can come up with a hatch that looks like that. And if you are offended by what I just said, make sure you have a shave before you come to class tonight. Here we are. Okay. So that's how we show welds. We're going to talk about welds in a second. There's another thing we have to do with welds, and that's show a weld symbol. I'm going to show you part of how to do that symbol. You're going to have to work out the rest of it yourself, which means it's in the mark. There's some additional information on bolts. you're welcome to read that if you want to, or it doesn't have any massive bearing on this course, but you may want to use some of this in your notes when you're calling up the box. This is how we do our dimensions when it comes to some examples of dimensioning to holes. I've only put that in there as an example of how you may like to do your detail. You're going to do one detail of that plate, and I haven't quite worked out where the second detail is going to be yet, but we're talking about assignment 4 here, by the way. I think the assignment explains exactly where you need to put it. Okay, we've got some common terms used in structural steel and some good explanations of what they are and where you would find them. The ones I've picked on for the multi-choice: girts, purlins, and a common Kiwi word, chock. Not chuck, chock. Chock is a small wooden block to resist thrust or pressure. So it's usually put between two other steel members and it reduces pressure. Another thing to remember is a splice, and a splice is usually used with timber, and it's used for lengthening, not strengthening. Other names you'll come across in other courses. So they're the 4 things that I can remember are questions in the test. So they're the 4 things I would recommend trying to learn. I'm not saying it's exclusive of those, but they're the ones that I remember.
Is that only for material?
I said that an important thing to remember, because I know in the timber there's a question on lengthening, splicing. You can splice steel and then weld it. It's much more common to do it with timber. The thing is, in terms of surveying, all these different names for things on site, when you turn up on site, sometimes you get told to, take shots to very high pieces of steel, and somebody's got to climb up there and do reverse shots and all sorts of things. And you've got to know your steel members if you're workers in construction, because you're shooting for them all the time and taking dimensions. The most important thing I found with steel work was they wanted you to determine the height to boundary as soon as possible before they put the steel members in place. Because if they did it once, they bolted them all together, it's too late. Okay? Next thing you know, you've got a legal fight on your hand with neighbours, etc. So the little amount of surveying that I did on construction sites, it was pressure work. We had to get there, get it done and get an answer to them before sort of 5 o'clock that night. Welding. This is how we determine a weld symbol. You are required to do a weld symbol for a 6mm weld, which I've written over there somewhere. 6mm weld. Fillet weld. The next section of notes goes quite deeply into all the different types of welds you can do. I could have been mean, I could have made you do a butt weld. I could have been even more meaner and made you do an intermittent MIG weld or something like that. I've stuck to a very common weld and a very common symbol on structural drawing. So this is the symbol here. This T will be replaced by the number 6. Just told you. Okay? Put a 6 here, put that there. Put this line here, The circle means all round symbol. That means the weld is all round. That is the weld we're doing. You have to decide whether it's an all round weld or not. Be careful and look at the notes. This little golf flag means on site. I've already told you today, if you review the tapes, I've already told you whether it is an on-site weld or not. It's about this high. The angle goes down between two plates. Would you weld that back in the factory and deliver it to site, or would you do the welding on site? Remember that bringing welding equipment to site produces its own problems. You've got to have, you've got big explodable gas tanks that you've got with you. There's sparks flying everywhere. You've got inquisitive Unitech students trying to look through at what's going on. Personally, I'd do as much as I could in the factory, actually. So the only thing left is what we call is these symbols here. So you have to decide whether there's a circle there, and you have to decide whether there's a golf flag there or not. I've already told you you're going to have the number 6 there. There are 3 options. That looks like a shark's or an upside down shark, or that. And as we go on in the notes, things may become a little clearer. Yep.
So that little golf flag, there's like a funny flag drawn on there, but yours is like you did now.
Will it be filled in?
Will it be straight or?
Oh, sorry, I got that flag around the wrong way. You're right.
Like a cross section.
If you decide to put it in, make it like that. If you would rather take the advice of the gentleman in the front, second row over here, then you won't have a flag at all. But he could well be right. Now I'm going to show you some, starting with what a weld looks like. So we use welding as a way of joining up 2 pieces of metal, but it doesn't necessarily mean it's stronger. When we talk about a 6mm weld, we're talking about the width of this piece here. Okay? So it doesn't necessarily mean it's perfectly 6mm all the way along, but the welders, and you can get some very, very good welders, their aim is to try and to stick to that approximate dimension. Okay? When you're putting your holes in this plate over here, remember the angle doesn't go through the plate, so you don't have to use the angle as a minimum or maximum. But you don't want to put the holes too close to it, because you won't get a crescent in there to tighten up the nut. And I think older students here will know exactly what I'm talking about. Well, if it's not a crescent, it could be a socket. So I would say from there, allow 6mm, plus maybe another 6 to 8mm. So let's call that 15mm minimum away from the angle, so you can tighten up the nut. So although your minimum and maximum are taken to the edge of the plate, you still have that restriction of keeping a good 15mm away from the angle. Okay? So here's some of your weld symbols. And you can see here that this triangle I was talking about, when it's pointing down, it means that the weld is only on the arrow side where you pointed it to. If it's pointed up, it means the weld is on the other side of the arrow. and if it's like this, it means the weld is on both sides to the arrow. There's your side weld and your round weld. And there's some little wee diagrams here which are quite cute, and they do show you exactly what the weld is and what the symbol is for that type of weld. I'm not going to do much more. I'm probably giving away too much there. Something that's on the marking sheet. So in each case here, it shows the type of weld and how we would call it up. When we have intermittent welds, they get an extra number in them. Actually, there's way too many clues there. Okay. There's a whole extra chart here of different types of welds, your fillet welds, your double welds, your seal welds. And here's my friend at the back there with the beard that was getting all upset about it. Yeah, so here's how we represent the plan view of a weld. Not the sideways view. The sideways view we use the symbol. The plan view we use the schoolboy's beard.
Is that a cheerleader?
Okay.
Receiver dono.
How do we? Have we got time? Yes, we have got time. I'll take it to the max. Then we can have a free lap tonight. Okay, and tomorrow.
So we're going to say we.
All right. I also need to.
किसको उठा लो किसके भी उठा लो इसमें हमारा
I can
नाम
start
भी
with that if you need to. I'm going to rub that board out. So while I'm just getting ready here, I'll be about 2 minutes. And we'll take up the next part of our lab doing a small project.